We have seen how we can train protein transformer network encoders for self-supervised prediction tasks, namely masked language modeling. This results in general protein representations that we can use for many different prediction tasks. In this video, we will shortly look at how we can train encoders for a specific prediction task that we are interested in to obtain protein representations that are even more useful for us. Let's do a short recap first of the self-supervised training that we have considered so far. We randomly mask approximately 15% of the amino acids in the input sequence and train the model to predict the type of the masked amino acid. This results in a meaningful amino acid representation that contains structural and functional information. After training, we can finally get a single protein representation by calculating the element-wise mean of all amino acid representations. The advantage of this method is that we can generate meaningful protein representations even for prediction tasks where we don't have a lot of labeled training data. The disadvantages of this approach is that we did not train the model for a specific task, and therefore we cannot be sure that the resulting protein representations contain all information that is relevant for our prediction task. A further disadvantage is that simply taking the element-wise mean over hundreds of amino acid vectors results in information loss. Specific details about the sequence, such as the exact order of amino acids or local patterns, might not explicitly be captured in the average representation, even if this information is relevant for the prediction task. Assuming we have a prediction task with a large training data set, how can we overcome these limitations? We can train such a transformer network encoder that we see here for the specific task that we are interested in and force the model to directly store all the task relevant information in a single vector. Let's have a look at how we can achieve this. First, we notice that we added an additional token to the input sequence, which we named CLS, which stands for classification. In the end, we want to use the updated representation of this token to make a prediction for the whole protein. In the beginning, this token doesn't store any useful information, only the information that this is the classification token. However, by passing the token embedding through the encoder together with all the amino acid representations, this token gets updated by using information about all amino acids in the sequence. We can train the model to use the updated CLS token that comes out of the transformer network encoder to predict a property of the protein using a fully connected neural network with this vector as the input. The variable that we want to predict is here denoted by y. For example, we could train the model to predict the optimal pH value of proteins. In this case, we would train the model to minimize the mean squared error between the predicted optimal pH for protein and the experimentally obtained optimal pH. When we train this whole model end-to-end, which means we adjust the parameters of the encoder and of the fully connected neural network simultaneously, we force the model to store all the protein information that is relevant for solving the prediction task in the updated CLS token representation. Training the model in this way, we get a task-specific protein representation by extracting all the information from the protein sequence that is relevant for this particular task. When training the protein language model for a specific task, you wouldn't typically train the whole model from scratch, but instead you would use the parameters of the transformer network encoder that was already trained for the masked token prediction task. This way, the model has already a set of useful parameters and has already learned to generate meaningful amino acid representations and to extract information from their interactions. This makes it much easier to train the model for specific protein property prediction tasks. After we trained this model, we have two different options. Since the model was already trained for our task of interest, we can simply use this model as our final prediction model. However, sometimes you get better performance results if you extract a protein representation from this fine-tuned model and use it as the input for another machine learning model, for example, a gradient boosting decision tree model. To do this, we can extract the updated CLS token representation for all proteins in our data set, having now task-specific protein representations that were generated by aiming to extract all information from the protein sequence that is relevant for solving a particular task. As I said, the token that we add for this task is called CLS, which stands for classification, because it was first introduced in the natural language processing domain for classifying sentences. So the concept of adding an additional token at the beginning of the sentence that is then used for downstream prediction tasks comes from classifying sentence, and hence this token is called a classification token, although we can of course use it also for regression tasks such as predicting optimal pH values for proteins. Fine-tuning a full protein transformer encoder quickly becomes memory intensive and slow because we have to adjust millions or even billions of trainable parameters. Low-rank adaptation, or LoRa, avoids that cost by leaving each original weight matrix completely unchanged and learning only a compact correction for the weight matrices involved in the attention function. Concretely, for every attention function or every attention matrix W of dimension d times d, we introduce two much thinner matrices A with dimension d times r and a matrix B with dimension r times d, where the rank r is far smaller than d. During training, we optimize A and B so that their product A times B captures the task-specific change delta W, and we add this update to the frozen matrix W. Given our new W equals our old W plus A times B. The matrix multiplication of A and B results in a D times D dimensional matrix, which means we can adjust every entry of W if necessary. But because A and B together contain only 2 times D times R parameters instead of D squared, and because R is much smaller than D, we reduce the number of trainable weights massively and the GPU memory they occupy, while still letting the model adapt its attention patterns to the new prediction task. In the diagram, the separation is shown by the large blue square for the frozen W and the green rectangles for matrix A and B. At inference time, we can merge the learned low-rank update into W, so the model runs just as fast as the fully frozen backbone, but now carries the information needed for the specific, for example, protein property that we trained on. This table highlights that only 3 parts of the networks remain trainable: the newly inserted LoRa adapters A and B, and the final prediction head that uses the updated CLS representations to make predictions, and optionally additional LoRa blocks in the feed-forward layers. All original model weights, the embedding layers, and the layer normalization parameters stay fixed unless deliberately decided to do it otherwise. We now consider a practical example that illustrates how much LoRa reduces the number of trainable weights. Imagine an attention weight matrix with a hidden size D of 1024. If we decide to fine-tune this matrix directly, we would need to update more than 1 million parameters, because a 1024 times 1024 matrix has that many entries. With LoRa, we can choose a low rank, for example R equals 8, and introduce 2 thinner matrices A and B, each of them containing only 1024 times 8 equals 8,192 parameters, so together they add up to 16,000 new weights. Since all original weights stay frozen, the optimization now updates approximately 98% fewer parameters, while still allowing the model to adjust its attention patterns. This drastic reduction has 3 important benefits. First, memory usage drops sharply, which means we can fine-tune large protein language models on much smaller GPUs or fit more sequences into each training batch. Second, because the pre-trained weights are never completely changed, the information captured during pre-training is preserved. We only add a small task-specific correction on top of it, rather than risking to override the representations that were learned from billions of amino acids. And third, the training loop becomes faster because the optimizer handles a far smaller set of variables. However, there are trade-offs. A low-rank update is less expressive than full fine-tuning, so performance can lag behind on tasks that require extensive reconfiguration of the model. We also introduce a new hyperparameter, the rank R, that has to be selected carefully. Choosing R too small, the model cannot adapt, and choosing it too large, we lose many of the computational savings. And finally, while inference speed remains almost unchanged, after the low rank update is merged into the frozen weights, the implementation is a little bit more complex because the training phase needs to add these A and B matrices, and after training we need to integrate these adapters back into the main matrices W.